So in this video on projectile motion, what we want to do is to be able to prove the general results. So rather than using just numbers, we're going to use letters and be able to make formulae for projectile motion. So the first one we're going to look at in exactly the same way as we have done before. And that's, we're going to look horizontally and vertically at the motion of a projectile. And horizontally, it's exactly the same. So if we have something projected with initial speed u at an angle theta to the horizontal. Horizontally, it has no acceleration. We're going to call the time of flight t. Its velocity is u resolved horizontally, so it's u cos theta. And s, the displacement or the distance here, is I'm going to call r for the range, just how far it goes. Vertically, I'm going to treat up as being positive because initially the particle is projected upwards. So the acceleration is due to gravity down, so it's minus g. The time of flight is t seconds. This time we resolve vertically, so it's u sine theta is the initial speed, or the initial velocity. And just need to be careful here with the displacement vertically. As it goes up and then comes down again, you can see its vertical displacement is 0. So, putting those into our UVATS equations, s equals ut plus a half at squared, and just looking vertically to start with. We saw that s was 0, that its initial speed was u sine theta, and the time with capital T. And again, putting in for that into a half at squared, we get this too. You can see that t, there's a factor of t we can take out there. And because this is equal to 0, it's like a quadratic equation. We can say either the first factor t equals 0 or this factor equals 0. Now t equals 0 is when it starts. So the time of flight that we're looking for, then we can rearrange this to get half gt is u sine theta and find that u sine theta divided by a half g is equal to t. And dividing by a half is the same as multiplying by 2, and we should put that 2 on top. And so we can see that we can get an equation here for the time of flight. T is equal to 2u sine theta over g. Now, we've looked vertically. Looking horizontally, we know that distance is equal to speed times time. And the distance that we're looking for is r, or the range of the flight. And the speed was u cos theta. We've just worked out that time is 2u sine theta divided by g. That's what we worked out in our previous proof, the time of flight. Putting that all together, r is 2u squared sine theta cos theta over g. Now what we're then going to do is take the 2 sine theta cos theta, because I know that 2 sine theta cos theta is a double angle. And we saw that in the pure maths, that's sine 2 theta. And so we can rearrange that now as u squared sine 2 theta over g. And so this is the range of a flight if it starts and finishes on a horizontal ground. Now, just something to note, the maximum range then is going to be u squared over g. In other words, when sine 2 theta equals 1. Because we know that the maximum value of a sine function is 1 and the minimum is minus 1. So for that to be the maximum, sine 2 theta has to equal 1. And that happens when 2 theta is 90 degrees or theta is 45 degrees. So our maximum range will happen whenever the angle of inclination, the angle of trajectory, is 45 degrees. And then the range will be u squared over g when we do that. Now, this is sometimes called the equation of trajectory, and rather than finding maybe the range of flight or the time of flight for one complete section, maybe when we're found, we're going to consider here a point P at xy. But again, we're going to look horizontally and vertically. And horizontally, again, a is 0, there's no acceleration. The time of flight is capital T, we're going to call it here. The initial velocity is u cos theta, and here we've got s is equal to, that's s equals x. You can just maybe not quite make that out, but x is the x coordinate of this point that we're considering. So distance is speed times time. So the distance, horizontal distance, is x, u times t cos theta. Now this t is different from the one we proved last time, because that capital T was the time of flight to go from here to here. So just need to be a little bit careful here. So capital T, we rearrange that to get the x over u cos theta. Now, let's use that in the vertical component, because vertically we know that that if I'm treating up as being positive, then vertically the gravity is negative, so it's a is minus g, time of flight is t, the initial velocity u sine theta. This time, because of the way that we had treated that, we treated this as the point x, y. When we're looking vertically, that distance there is just y. So when we use s equals ut plus a half at squared, y is equal to u sine theta t minus g over 2t squared. Now again, we find that from horizontally that t was equal to x over u cos theta. So we're going to fill that in for t here and t squared here. And this is where this comes from. X u sine theta t over u cos theta minus g over 2 t squared. So there's x squared and u squared cos squared theta. And at the minute it looks a wee bit of a mess, so we need to tidy it up a wee bit. And that's not too hard. We know that sine theta over cos theta is tan theta. This u and this u cancel out, and so we're just left with this fraction as x tan theta. Over here we can get that that's gx squared over 2u squared times 1 over cos squared theta. And that 1 over cos squared theta is the same as sec squared theta. And finally, we're nearly there. Sometimes you'll see this as the equation of trajectory, but we also know that from our trig identities that sec squared theta is 1 plus tan squared theta. So quite often you'll see this sec squared theta replaced with a 1 plus tan squared theta. And that's very helpful because it means that everything is in terms of tan theta, which is quite neat. So the equation of trajectory, if you want to find any point on that trajectory, xy, then y equals x tan theta minus gx squared over 2u squared upon 1 plus tan squared theta. And we need to be able to prove all of these equations that we've done. So the equation of trajectory, we need to be able to prove the range of a flight and its maximum range. And we need to be able to find the time of a completed flight as well.